So again, continuing with molar solubility, KSP. Here we want to calculate the molar solubility of strontium fluoride in a 0.05 molar solution of iron 2 fluoride. And it gives us the KSP. So again, the dissociation of strontium fluoride looks like this. Now initially we're going to have some fluoride in solution. So we need to determine the concentration of fluoride that is initial in the solution. Because here you see the K expression, strontium fluoride, or strontium times the fluoride concentration squared. And so the original fluoride concentration, or the initial fluoride concentration, is going to be 0.1 molar, because here we have FeF2. For every 1 mole of FeF2, we have 2 moles of fluoride. So initially, we're going to start out with something like this. So notice that with fluoride, we have 0.1 and not 0. And then we have the change, equilibrium. And again, for the solid, we can disregard it. Since X is going to be a lot smaller than the initial concentration of fluoride, we can also negate the plus 2X. So now we have the equilibrium expression. We can solve for X. And so here the molar solubility of strontium fluoride is 2.6 times 10 to the negative 7. Again, we can negate the plus 2X because the value of X is going to be a lot smaller than the initial concentration of fluoride. Now the next one had 2 parts, and we're going to use iron 2 sulfide. It gives us the KSP of iron 2 sulfide. First, it asks to express the molar solubility expression for iron 2 sulfide. So again, we start off with the dissociation of iron 2 sulfide. Now what you have to remember is that sulfides are special, meaning that when the sulfide ion is produced, it's so basic that it's going to automatically start reacting with water. So we have this second equation as well. So as soon as we produce sulfide, since it's so basic, it's going to react with water to form bisulfide ion and hydroxide. So the overall reaction is this one right here for sulfide, for iron 2 sulfide. And it would be the same regardless of what sulfide. So any sulfide you use has this secondary reaction, and this is the overall reaction for a sulfide. So again, we set up our ice table. We initially start with none of the product. We have the change and an equilibrium. Again, we can negate the 1 minus X because it's the solid, and we get the molar solubility expression equal to X cubed. So K equals X cubed. If you solve for X, that'll tell you the molar solubility of iron 2 sulfide. So in B, we want to calculate the molar solubility of iron 2 sulfide. So again, we found the expression in the previous problem. We set X cubed equal to 8 times 10 to the negative 16. And we get X equals 9.3 times 10 to the negative 6. And so that would be the molar solubility of iron 2 sulfide. In C, it wants us to calculate the molar solubility of iron 2 sulfide in 0.05 molar iron 2 nitrate solution. So again, we set up our ice table. So this is the overall reaction that's occurring for iron 2 sulfide. So initially, we start with 0.05 molar of iron 2 plus, because you see here iron 2 nitrate, there's 1 iron for every 1 formula unit of iron 2 nitrate. Then we have the change. So we get rid of some reactant, we form product. Now again, we can negate the 1 minus X, and we can also negate the plus X, because whatever X is going to be a lot small compared to 0.05. So then we set up our expression. And solve for X. And X is 1.3 times 10 to the negative 7. So notice how the solubility of iron 2 sulfide decrease when we have a common ion present. We compare it to water was 9.3 times 10 to the negative 6. Iron 2 sulfide is 1.3 times 10 to the negative 7. So whenever a common ion is present, it decreases the solubility. So next we want to know which of the following salts would increase in solubility by adding a strong acid. So let me show you an example of this. Let's say, for example, we have, I don't know, copper fluoride. And we wanted to increase the solubility of copper 2 fluoride. What we can add is a strong acid. So what happens is when we add a strong acid, say HNO3 for example, since fluoride is weakly basic, it reacts with the acid or the strong acid to form weak acid. And so what happens in this is that as you decrease the concentration of F minus, you're going to cause Le Chatelier's principle to take into effect, and you're going to shift to make more product. So when you add a strong acid to a salt solution that contains a weakly basic anion, the acid will react with the anion to form weak base, and therefore driving the dissociation of your solid according to Le Chatelier's principle. So what we're going to be looking for is to know which salts would increase the solubility when adding a strong acid. We want to see which ones have an anion that's weakly basic, aka comes from a weak acid. So we look at PbCl2. Cl is not a weakly basic anion because Cl or chloride comes from a anion of a strong acid. So that would not be one. Magnesium phosphate, well, phosphate comes from the weak acid phosphoric acid, and so this would be one that you could increase its solubility because phosphate is a weakly basic anion. Next we have silver cyanide. Again, cyanide is the anion of a weak acid. It's not an anion of a strong acid. So therefore, since it's an anion of a weak acid, it would increase in solubility when you added a strong acid to it. Next we have copper iodide. Iodide is the anion of a strong acid, so therefore this would have no effect when you add a strong acid to it. And lastly, we have barium carbonate. Carbonate is the anion of a weak acid, so therefore the solubility would increase when you add strong acid to that solution. So again, the reason the solubility increases is because according to Le Chatelier's principle, if you decrease the amount of product, it's going to shift to put more reactant into solution. So next we can actually calculate the pH of weak base solutions such as sulfide. And so the way we do that is, again, we write the dissociation of sulfide. We get this overall equation. And then when we want to calculate the molar solubility of nickel sulfide, sorry about that. It should be nickel here. Copy and paste error right there. And this should be nickel 2+. And so you see we get this expression for K. So the equilibrium constant is equal to x cubed because you see at equilibrium we have 3 species. They're all 1-to-1 mole ratio, so everything is x. So when we solve for x, we get the concentration of hydroxide at equilibrium. now that we know the concentration of hydroxide, we can find the POH and then find the pH. So the pH of this solution at equilibrium would be 8.83. Now, since hydrogen sulfide or bisulfide anion is weakly or is basic, you could add acid to the solution to increase the solubility of your compound. So this was the pH of a weakly basic or a weak basic anion. Next, we want to calculate the pH of a partially soluble hydroxide. Here we have magnesium hydroxide, KSP 6.3 times 10 to the negative 10. So we write the dissociation of magnesium hydroxide. Again, initially there's no product present. Now here you'll notice for every 1 mole of reactant, we get 1 mole of magnesium 2 plus 2 moles of hydroxide. And then we can always negate the 1 minus X because magnesium hydroxide is a solid. We get this to be the K expression. And again, the reason we squared is because the KSP expression is squared. So we square the 2x, we multiply it by x, it equals K. So we have 6.3 times 10 to the negative 10 equals 4x cubed. We get x equals 5.4 e to the negative 4. Just double check. Hold on a second. Oops, made a boo. Oh, wrong one. Wrong. Hold on. Yeah, we get 5.4 e to the negative 4. Now this is x. To get hydroxide, we have to multiply it by 2. Oops, I didn't show that. So to get the hydroxide ion concentration, I thought I had shown it. Apparently I didn't. Because remember, hydroxide is 2x, so 2 times x. So we get 1.08 e to the negative 3. And so that's the hydroxide concentration at equilibrium. Then we take the negative log of it, and we subtract that POH from 14, we get a pH of 11.04. And so again, this is when you're wanting to calculate the pH of a hydroxide at equilibrium. This is how you would go about solving it.